Good afternoon, friends. Up till now, we have discussed in the series of bending stress in beams about what is the bending stress, how the bending stress can be found out, and how the formula of bending stress can be derived that we have been studied up till now in the previous series. So, we learned in the previous sessions about types of supports and beams, types of loads acting on the beam, determination of support reactions, plotting of a shear force and bending moment diagram of statically determinate beams, concept of bending stress and section modulus, concept of bending equation and moment of resistance. So the objectives of today's session is to draw the bending stress distribution diagram and calculate the maximum bending stress in a given beam, calculate the bending stress with symmetrical and unsymmetrical sections. Let us revise the things that we have studied up till now in the previous classes. If we take any section of a beam and consider the free body diagram on either side, we find that there must be three internal stress resultants at a section in general to maintain the equilibrium of free body. These three are bending moment, shear force and axial force. Here in this series we are discussing the effect of bending only. Let us understood this concept by taking a simply supported beam with the subjected with the external loading. If we take any section on this particular beam and if we plot the free body diagram of any of the section, let the left section, then at this section the three component, that is the bending moment, shear force and axial force, will be developed. The effect of this bending moment is to develop the compressive force at the top of the section and the tensile force at the bottom of the section. This leads the bending stress in a beam. Hence, under the effect of lateral loads, the beam bends and the longitudinal axis takes a curved shape. The beam produces an internal resisting couple to balance the bending moment due to the applied loads. This couple is generated by the normal compressive and tensile forces in the section. Let us be understood this taking a concept of a simple beam over here. Beam, when it is subjected to an external force that causes the compression on the top of the portion and tension on the other side. This also causes beam to deflect. Now let us be understood the equations that we derived. We derive a bending equation, that is m is equal to E over R into I. In short, it is m over I is equal to E over R. But we know F over Y is equal to E over R. So combining these three different terms together, we obtain a bending equation is as m over I is equal to F over Y is equal to E over R. This equation is known as the bending equation. We also found the Z, that is the section modulus, is equal to I divided by Y max. Let us revise once again what is the section modulus and how this section modulus can be found out for four different known section. So section modulus is defined as the ratio of moment of inertia of a section about the axis to the outermost layer from the neutral axis, that is Z is equal to I by Y max. Mathematically, where I is the moment of inertia, Y max is the distance of outermost layer from the neutral axis, then Z is equal to I divided by Y max. Now M is equal to F max into Z. Here M is the moment of resistance offered by the section, that is, it is the maximum bending moment. Also, moment of resistance offered by the section is maximum when the section modulus is maximum. Hence, section modulus represents the strength of the section. Let us revise the four different sections. The first is the rectangular section, and we found out that the Z is equal to 1 by 6 BD square. As we know that I is equal to BD cube by 12 divided by D by 2, we got the BD square by 6. For hollow rectangular section, we got Z is equal to 1 by 6D bracket BD cube minus small bd cube, where capital B is the outer width of the section, capital D, that is the overall depth of the section, small b and d are the inner dimensions of the hollow rectangular section. For full circular section, Z is equal to pi by 32d cube. Now it is interesting to note that Z is equal to I by y max, where I is the pi by 64 d raised to 4, while y max is the d by 2, so we got pi by 32 d cube, that is the Z for circular section, while for hollow circular section it is Z is equal to pi by 32 capital D bracket d raised to 4 minus d raised to 4, where capital D is the outer dia and d small d is the inner dia of the section. Now, up till now in the previous class we have solved the numericals. From that numericals, where our intention is to find out the bending stress, or alternatively our intention is to find out the load by using the bending equation. So let us revise one simple problem that we have solved in the previous session, that is a square beam of size of 20 mm by 20 mm in section, and the length of that particular beam which has been given to as 2 meter, which is simply supported. Now if this beam fails when the point load of 400 Newton which is applied at the center of beam, so what is the thing which is known to us? We know that is the length of the beam, 400 Newton load which is applied at the center, and our beam will fail. Then the question is about what will be the uniformly distributed load per meter length will break the cantilever beam of the same material but of the size of 40 mm wide and of 60 mm deep with the 3 meter long. Now in this particular beam, first portion that gives us about the simply supported beam with the center point load. So now if we come to this tabletop, then in this particular beam, the first simply supported beam which has been given to you of length of 2 meter and the center point load of 400 Newton which has been given to us. The section which has also been given to us of size of 20 mm by 20 mm. So we can able to find out at what stress the beam will fail by using the equation M over I is equal to F over Y, where M, which can be found out with the formula WL by 4, as the simply supported beam with the center point load 400 Newton which has been given to us. I is nothing but 1 by 12 BD cube when B and D are the same, that is of 20 mm and 20 mm. Now thing is about F and Y. Y is nothing but 20 by 2, that is the Y maximum, and unknown part is F. Now once we found out the value F by using this simple equation, we have to go with the second part. So if we come to this PPT, then you can visualize that Z, that is the section modulus BD square by 6, we can find out this value. M is equal to WL by 4. If we convert in terms of Newton into mm, we have to multiply by with the figure 1000, and if you are using the simple figure M over I is equal to F over Y, and if it's simplified M is equal to F max into Z, we can find out the F max is the 150 Newton per mm square. That is our first part that we can achieve. Now if we go to the second part, so come to this particular tabletop. Here the cantilever beam which is given to us, it has been stated that this cantilever beam, which is made up of the same material, means the F max that we have already found out with the help of the previous bending equation, that is the 150 Newton by mm square. The same thing we can use in this particular beam. The section for this, which has been given as 40 mm by 60 mm, the length which has been given as 3 meter. Our intention is to find out this UDL, the value of UDL. Let us, it is W kilo Newton per meter. Our intention is to find out what is the value of W by using a single equation, m over I is equal to F over Y. I we can easily found out by using the rectangular section which has been given to you, so it is 1 by 12 BD cube. The value F, which we have already been found out from the previous equation, that is F max is equal to 150 megapascal, and Y is nothing but 60 by 2. So as we solve the same problem in the previous case, so I have to go slightly faster way. Please revise the things that we have studied in the previous class. M, now this is a cantilever beam. What is the value of M max? M max is nothing but W L square by 2. L is known to 2 is known as, only unknown parameter is W from full equation. Let us come to this table top, on this PPT. Now let W, that is the UDL per meter, run. Maximum stress will be the same as of the simply supported beam, that is of 150 megapascal, that is Newton per mm square. B, D and L for a given beam which is given to us in this case. Then Z we can found out by an equation, B square by 6. M is equal to WL square by 2. If we convert it in terms of Newton into mm, we can found out 4.5 W multiplied by 1000. Then by using single equation, M is equal to F max into Z, we can able to find out W is at ease of 800 Newton per meter. So now here I would like to say one statement. It is very easy for us to find out any kind of solution by using simple single equation, that is of M over I is equal to F over Y is equal to E over R. So now let us, today we are going with the next problem. Number 7 problem. A simply supported beam carries a UDL of 40 kilonewton per meter over an entire span. The section of a beam is of a rectangular having a depth of 500 mm. If the maximum stress in the material of the beam is of 120 megapascal, 120 Newton per mm square, and the moment of inertia of the given section is 7 into 10 raised to 8 millimeter raised to 4. Interesting point, the value of I which has been given to us. Find out the span of the beam. Very good problem which has been given to us, and we have to solve with the using the concept of bending stress. Let us refer the problem once again and found out which kind of the data which has been given to us and what is our unknown parameter, what the thing we have to found out in this particular problem. So let us see the problem once again. Given beam which is of simply supported beam, please refer the PPT. The given beam is of simply supported beam, and the UDL which is acting W, that is of 40 kilonewton per meter. If I will multiply with the 1000, it is of 40,000 Newton per meter. The depth of a section which has been given to as 500 mm. The maximum value F max which is given to as 120 Newton per mm square, while the I is 7 into 10 raised to 8 millimeter raised to 4. Let L, that is the span of the section, that is the known parameter. Now section modulus Z we can find out with the equation I by Y max. I, which is known to us, 7 into 10 raised to 8, y max, that is d by 2, that is 500 by 2, that is 250 mm. By using the simple calculation, we can able to found the value of z is the 28 into 10 raised to 5 millimeter raised to cube. Now, maximum bending moment for a simply supported beam carrying UDL W per meter run, which is given by an equation WL square by 8, where W, that is the UDL which is acting on the throughout the beam. So we can able to find out 40,000 into L square by 8. So 5,000 L square. The answers in terms of Newton per meter. If we convert in terms of Newton into mm, I have to multiply by 1000. Now if we can use m is equal to F max into Z, m is known to you, 5000 L square multiply by 1000. F max is known to you, that is of 120, and Z is nothing but 20 into 10 raised to 5. And we simplified this one, we can able to find out L square value is of 2.4 into 28. So we can able to find out L is 8.197 meter, that is of approximately 8.2 meter. So here in this problem, it must important for you to know this value, that is the maximum bending moment for a simply supported beam having an UDL, that is of WL square by 8. That should be known to you. If you do not know this value, then you have to find out by using the concept of bending moment. I wish you have understood this particular problem. Let us go with the next problem. Number 8 problem. A timber beam. Here it has been specified beam made of timber of a rectangular section, which is to support a load of 20 kilonewton UDL over a span of 3.6 meter when the beam is simply supported. Very good thing which has been given to you. Here it has been stated that 20